In this video, I wanted to go over a practice FRQ from AP Physics C, Electricity and Magnetism. I don't know what year this is from, but it's one of the practice FRQs we were given to prepare for our upcoming test on circuits, including RC circuits. So this is another RC circuit problem that I wanted to walk through because it is very interesting and good practice. So let's just dive right in. So in the circuit above, an ideal battery of voltage V initial is connected to a capacitor with capacitance C initial and resistors with resistances R1 and R2, with R1 being greater than R2. The switch S is open and the capacitor is initially uncharged. So part A is asking us to sketch the charge Q on the capacitor as a function of time after the switch is closed at time t equals 0, and label any intercepts, asymptotes, maxima or minima with the values or expressions as appropriate. Okay, so the first thing that we need to know is our equation for charge in our circuit. So Q is CV. So this, yes, this is the equation for our charge in our capacitor. And the charge in our capacitor is going to approach this value after a certain amount of time has passed. However, we're in an RC circuit, so what our graph is actually going to look like is not like a linear relationship. The key equation to remember here is this one. So this is our standard equation for, in an RC circuit, what our charge is going to look like. And we derived this equation in the last episode of this channel. So if you would like a more in-depth explanation for how we got to this equation, please see the last video. So based on this equation, we can recognize a couple of things. We should recognize that this is an exponential graph, and because we're subtracting E, it's going to look something like this. And well, not exactly exponential because it's more of like a logistic looking ish equation because we level off at a certain value. And the value that we level off on, otherwise known as the asymptote, is again back related to this equation. So if we think about what this will look like, this term will look like as t approaches infinity, as we continue on, we can just, right, it looks like that. So 1 over e to the infinity, basically, and that's going to go to 0. So this entire thing is going to 0. So our Q is essentially going to be equal to EC. So that's actually what our asymptote here is going to be, if I can draw that. And our electromotive force in this situation is provided by V initial. So this is just going to be V initial times C initial as per the constants provided. So next, let's tackle part B. Part B is telling us to sketch the current through each resistor as a function of time and to clearly label the two curves as I1 and I2, and the currents through resistors R1 and R2 respectively, and label any intercepts, asymptotes, maxima, minima with numerical values as appropriate. So key thing to remember here, why is that? I is equal to dq dt. So basically, our graph of I is going to be, at least for resistor 1, which is the one that is directly connected to the capacitor branch, that is going to be the derivative of the graph that we drew in the previous equation. So the graph that we drew in the previous equation kind of had a increasing slope at first and then it started leveling off. So what that's going to look like is something like this, but less shaky and more accurate. And basically, this is our starting point, which is going to be V initial divided by R1. And basically, this is just the graph of the derivative of the graph that we just drew for Q versus T. Now, we have to make sure that we also draw the graph of resistor 2. So the thing that might trip you up here is that resistor 2 is also included in the circuit, but resistor 2 is actually parallel to the loop in resistor 1. And thus, it has pretty much no relationship with the capacitor. So it's not actually part of the RC circuit, so to speak. So the value for the current that it's going to receive is going to entirely be based on Ohm's law, which is V equals IR. So if we were to calculate that, V initial is equal to I2 R2, so V initial divided by R2 equals I2. And because R1 is greater than R2, it was given to us in part A, or in the description for the problem, we know that V initial divided by R1 is going to be less than V initial divided by R2 because of this statement that was given to us in the start of the problem. So we know that, I'm going to do this in red here, somewhere here. Ideally, you would give yourself more space to do this. We have our current. And important to note here is that our current actually is not changing in this situation because it's being held constant because it's just based on Ohm's law. In our RC loop, like the loop that contains the actual RC circuit, our current is going to be changing because we're charging the capacitor, and the capacitor gaining charge is actually going to be affecting the rest of the circuit. So yeah, these are our two graphs, and make sure that we label this as I2. So we labeled everything, and now it's time to move on to part C. Tackle part C of this problem, which I personally found to be the most challenging part of this problem. So let's take a look. We were being given some additional information, and I redrew the circuit at the top just so that we can have a visual of the circuit at all times. So let's go ahead and read. The circuit is constructed using ideal 1.5 volt battery, an 80 microfarad capacitor, and resistors R1 is 150 ohms and R2 is 100 ohms. The switch is then closed, allowing the capacitor to fully charge. Then the switch is opened, allowing the capacitor to discharge. So the time it takes to charge the capacitor to 50% of its max charge is delta T sub C. The time it takes for the capacitor to discharge to 50% of its max charge is delta T sub D. Which of the following is going to correctly relate the two time intervals? So we can do this very simply by using an equation called the 50% equation. So this equation, basically, it gives us the amount of time needed to charge to 50% using our tau, which is our time constant. Now this time constant is a value that is used to compare different RC circuits. So this is actually equal to R times C. And ln2 is just ln2, it's a constant, approximately equal to 0.693. So we could just use this equation and be done with it and find out which time interval is greater. However, that is not what we're going to do. we're going to derive this equation so that we can truly understand where it comes from and why it works. Okay, so to derive this equation, let's start from our very basic equation, which we have for our charge for our capacitor, uh, or charge for our circuit in our RC system. So again, if you have not yet watched the derivation for this, please go ahead and make sure to do so because it'll really help with understanding where this equation comes from. So we have our standard equation, but one thing I want to call your attention to is that we can rewrite this equation like this. So basically what we did is we took the electromotive force times C and replaced it with a new variable called Q max. And Q max is the maximum charge that our capacitor can have. And the reason we were able to do this is that, as we know, as time approaches infinity, Q is going to approach E times C. So this is actually our max value. So now that we have rewritten the equation in this way, we can also solve for the value of T, which provides 0.5 Q max. Now, how do we do that, you ask? Well, we just do this. So we have very cleverly substituted 0.5 Q max because, remember, the question is asking us what is the amount of time required to charge the capacitor to 50% of its maximum charge. What is 50% of its maximum charge? Well, that's 0.5 times Q max. And now you will notice that we have Q max on both sides of the equation, so we can easily cancel that out. And we get 0.5 is equal to 1 minus e to the negative t over RC. And from here, we just have to do a little bit of solving and we can solve for t. And negative t over RC. Now we're going to take the log of both sides. And we get and boom, we have basically just derived the equation that we started off with, which was this one. So essentially, just remember that you can replace RC with tau, and negative ln 0.5 is just ln2. So we just derived our equation, which means we can now use it. Keep in mind that you can go through the derivation with the discharging equation, which looks like this, just for your reference. So we could go through this exact same derivation and we'd pretty much end up with the same expression for tau. And, sorry, not for tau, for TD. So what's the difference between this and that we'll get from the discharging equation? So the difference between these two is actually in the value of tau itself. So in our charging equation, the value of tau is going to be equal to R1, which is 150 ohms, I believe. Yeah. R1, which is 150 ohms, times our capacitance, and that's going to be the value for tau here. However, in our discharging equation, the value for tau is going to be the equivalent resistance times the capacitance, but the equivalent resistance has actually changed. Why has it changed? Let's take a look. While the capacitor was charging, while the system was charging, we only had one resistor truly contributing to the RC part of the circuit. That was R1, because R2 is on a completely separate branch, it's parallel, and has nothing to do with the RC circuit. However, once we start discharging the circuit, we remove the battery entirely, and we just have our connection between our capacitor and our two resistors. So in our new system, the equivalent resistance is basically the equivalent resistance of a series circuit system, series resistor system. And in a series resistor system, our equivalent resistance is going to be R1 plus R2. For our discharging. So that is the key difference between our equation that we obtained. So Tc, let's write this out now. T sub C is going to be equal to R, which is 150 ohms, which is R1, times ln of 2, times, we have to remember to multiply by the capacitance, and don't forget to multiply by 10 to the negative 6 because we are given our value in microfarads. So if we crunch the numbers, we get something like 0.00835 seconds. So remembering units is very important here. In this case, our units are going to be seconds. Okay, moving on to our discharging, tau is going to be equal to equivalent resistance, which was 250 ohms. So 250 ohms times 80 times 10 to the negative 6. And then to find TD, we want to multiply tau times ln2. And once we crunch the numbers, the value that we get for T sub D is going to be 0.0139. So you'll notice that T sub D is greater than T sub C. And this is our final answer. So to justify our answer, yeah, these two expressions match. To justify our answer, essentially, all the work that we have shown here is enough work to show. I'm not familiar with the AP grading guidelines. I think maybe if you just directly use this equation, you should be fine. But I feel good that we've derived the equation because now we understand where it actually comes from and why it is used. So, yeah. Okay, so in this video, I wanted to finish up our FRQ that we were working on by doing parts D and E in one shot. So let's take a look. So we want to calculate the current through our resistor R2 immediately after the switch is opened. And sorry, I didn't redraw the circuit here, so hopefully you have a picture of the circuit somewhere, or you have my other video open or something. Draw the circuit. It is good practice. So we want to calculate the current through R2 immediately after the switch is opened. So if you'll recall from part C, right after the switch is opened, our system is going to become kind of like two resistors in series. So our equivalent resistance is going to be R1 plus R2. And we can use simply Ohm's law for this now because our capacitor is kind of going to act like a voltage source because it's been charged. So we have V equals IR, and V is 1.5. And that's going to be I times 250 ohms. So we're going to get I equals 6 times 10 to the negative 3 amps, or 6 milliamps. Yeah, so make sure that you recognize why the voltage is going to be 1.5 volts. The capacitor at max charge is going to have the same voltage as our electromotive force. So that's why we use 1.5 volts, which was our voltage for the electromagnetic force for the capacitor. Okay, now that we did that, we can answer part 2, which is the current through a resistor R2 increasing, decreasing, or constant immediately after the switch is opened? So to answer this question, this is really a conceptual question. So we have to understand what is happening to the circuit as the capacitor discharges. So remember that in a capacitor, Q equals CV, and we're actually going to be losing charge because we're discharging. So our voltage is going down. Our voltage is going down, which means that our current has to be going down because our resistance isn't being changed. And the sum of the voltage inside of the loop has to always add up to 0 by Kirchhoff's loop law. So we know that as our voltage decreases as the capacitor discharges, we know that our current must also be decreasing. So that would be the reasoning for that. And for part E, we want to calculate the energy stored in the capacitor right after the switch is opened, and also calculate the energy dissipated by the resistor R1 as the capacitor discharges. Okay, so for energy stored in the capacitor, this is purely based off of the formula, which is E equals 1/2 CV squared. Really no way of getting around this question, at least not that I know of, without knowing the formula. So we just plug in our values for that. And our answer should be something to the order of 9.0 times 10 to the negative 5 joules. So that was pretty straightforward. Now this next part, part 2, is a little more tricky. So we need to calculate the energy dissipated by our resistor as our capacitor completely discharges. So when I see the phrase energy dissipated by resistor, first thing that pops into your mind has got to be power, because power is basically describing like the dissipation of energy through a circuit. So we can use calculus and power to solve this equation, but there's also a simpler way. So I wanted to show the simpler way to solve it and then show the way that involves calculus. So the simpler way to solve the equation recognizes that energy splits proportional to resistance. So what this means is we can calculate the ratio of R1 over R equal and multiply that by the energy that we calculated in the previous equation, and that should be the energy that's being dissipated by R1. So I found that this is a quite clever way of solving this problem, which avoids a lot of the bells and whistles of calculus that one can so easily get caught up in. So let's take a look at this method. So R1 over R1 plus R2, that's equal to 150 over 250, which is 0.6. And then energy dissipated by R1 is going to be equal to 0.6 times the total energy, which we calculated in part 1 of part E, and we get 5.4 times 10 to the negative fifths. Now this was the very easy way of solving this question. However, there is a more intense calculus-based way of solving the equation. We can do that by using our trusty old RC circuit charging equation. Or, sorry, our RC circuit discharging equation. So using this equation, what we're going to do is take the derivative of both sides. And that will allow us to find the current. So once we do that, recognize that our initial current is going to be 0.006 because we calculated that in part 1. And if we take the derivative of this expression, we are going to get e to the negative t divided by 0.002 because it's just going to be our, just use chain rule for taking the derivative. So once we do that, once we get this expression, we're going to use this expression to calculate our energy by calculating power. So kind of the way to do that is calculating the derivative of power over a certain amount of time, which is, oh, sorry, not the derivative, the integral. It's been a long day. So 0 to infinity of I squared of t times r dt. And notice that r is a constant because r does not vary with time because it's inherent to the resistors. Okay, so once we have this expression, we're just going to directly substitute this expression here. And so now we got to do some good old calc. So taking the derivative of, so this is kind of annoying. We're going to e to the negative t divided by or sorry, multiplied by 100, because if we take the derivative of that, it's gonna divide by 100. So just use reverse of chain rule to reason this out. So 100 e to the negative 100 t, because t divided by 0.01 is, of course, yeah. Once we get that, this is the antiderivative for that part of the expression. Sorry if this is confusing. This is just me working through good old antiderivatives. So 100e to the 100t. So yes, for the e portion of the um, integral, you should be, this should evaluate to 100e to the 100t. And once you have that, and you plug in infinity for t, because you're going from 0 to infinity, you don't really plug in infinity, but you evaluate as t approaches infinity. And what that's going to give you is this, um, yeah, so if you plug in infinity, whole thing goes to 0, but you're actually going to be subtracting. Sorry, had a brain fart there. But our bounds of integration are from 0 to infinity. So we're going to be going from infinity. So if you plug in infinity for t, then this entire thing just goes to 0 because infinity is in the denominator. And then you have to plug in 0 for t, which just gives you 100. And then this is the expression which actually will give you your answer, which is going to be 5.4 times 10 to the negative 5. And we take the absolute value because it's asking us the energy dissipated, so it doesn't really make sense for such a quantity to be negative, because how do you negatively dissipate energy? Like, that's not a thing. So yeah, two ways of solving the same problem, one way being a little more long-winded and complicated than the other, both equally valid, and you can choose whichever way you like on the test.